Well, thanks a lot, and thanks a lot to Miguel for inviting me here to talk about my work. So, as the title suggests, I'm going to talk about differential geometric problems in supergravity. So, first of all, I want to explain what's supergravity, because I will not assume that you know anything about supergravity. So, for those of you that have some knowledge, well, sorry. And the lesson I would like you to take home is why is supergravity interesting in differential geometry, or why it can be interesting in differential geometry, and what's the type of problems that you can find in supergravity and the type of mathematical tools that you need to address these problems. So to begin with, I need to just state the typical mantra about supergravity. So this is an informal definition, of course. That supergravity is a gravity theory bias under well, certain infinitesimal transformations generated by a streamer and satisfy several conditions. So, of course, this is far from being a mathematical definition, but it may give you an idea of what is going on. So, the context in which supergravity lives is that of general relativity. So, in general relativity, the basic equations, as you know very well, are the Einstein tensor of some Lorentzian metric G equal to modulo irrelevant constants. For us, the energy momentum tensor, which may depend on some field either sections, well, they are linear sections of bundles or connections, and there are other possibilities. These are the basic stuff. So supergravity is like this. So the basic equation is an equation of Einstein type. So this is of Einstein type. Which is usually written as in terms of the Ricci curvature equal to some other symmetric tensor. So this of Einstein type is the basic equation. But what happens in supergravity is that this guy here is not arbitrary. It needs to be supersymmetric. So this guy here needs to be supersymmetric, or SUSY for short, meaning that it needs to be preserved by the corresponding supersymmetric transformation together with the Einstein tensor. And of course, in supergravity, you also have equations for each of the fields. So at the end of the day, what you get is a coupled system of this form. You get some Einstein type of equation and some other equations for these fields, which I'm not specifying because the details depend on the particular supergravity under consideration, and there are many. Okay, so this is the basic equations of a supergravity. Okay, so locally, supergravity is defined through a Lagrangian. So locally, so let's say on some open set, which for us is going to be an open subset of R4, this is defined through a Lagrangian function, which goes from the configuration space of the theory on U to some function, and it can be written again schematically as being evaluated on fields of two types, and We don't need to know what that means physically, not that I will know how to explain it anyway, but mathematically, the situation is more clear in the following sense. So these bosonic fields let me begin with the fermionic. The fermionic fields are those that take values on a spinor value, which I will define in a moment. But at this point, it's enough to have just an informal idea of what it is, a bundle of spinors. And the bosonic fields are those that don't. It's a working definition for a mathematician. Those that don't. Okay. And then, as I was saying, supergravity, this Lagrangian needs to be invariant, rather, the equations of motion that follow from this Lagrangian needs to be invariant under some infinitesimal transformations that we call supersymmetric transformations. And again, schematically, these transformations, which are infinitesimal, so I write a delta epsilon, this is the spinor that generates the transformation, maps the bosonic fields into a combination of the fermionic fields. So this is a function of the fermionic field. This is a schematic. And similarly for this guy here. So in a sense, this transforms boson into fermions, fermions into bosons, and this is why this is called a supersymmetry transformation. This is what the founders refer to this as supersymmetry, because it went beyond the type of symmetries that were considered at that time, which never mixed this type of different type of fields. So, and then the requirement is that this is preserved in the sense of equations for motion. Very well. So the key point to notice now is that there is no mathematical theory of these structures. So even if I wanted to tell you what's the mathematical theory behind the type of equations you get from this Lagrangian and this type of, especially this type of transformations, there is no mathematical theory available, and probably is out of reach, who knows? But it doesn't matter, because for the type of problems that we are going to consider, we don't need to study the full structure of supergravity in the following sense. So, by the way, you can interrupt me at any point if you have a question. So, even though this structure, which is heavily studied by physicists, they don't care if there is a mathematical theory of these transformations or not, of course. But for the key point is that for applications to differential geometry and topology, we don't need to study the whole structure. So for applications, for application actually to let's say to mathematics, which is in this case differential geometry and topology, and to physics actually, or to most applications in physics, we don't need to consider the whole structure, because one is interested only in a particular class of solutions of these Lagrangians, which is obtained by taking the fermionic vector, namely all the fields that take values in this abstract spinor bundle, equal to 0. And this is called a bosonic configuration. since this is a classical or semi-classical theory of gravity, so physicists will say that fermions are not observed macroscopically, even fundamentally. So therefore, you take these suckers equal to 0. And when you do that, you get what's called a bosonic truncation. I said this is always consistent, and you may be disappointed because what's the point in studying a supersymmetric theory if you then go and truncate the fermions, which are supposed to be the main ingredient of the theory? Well, the thing is that even if you remove these fermions by truncating them to 0, supersymmetry, my dear Susie, leaves an imprint. So it doesn't disappear in the following set. Now our Lagrangian, we get a bosonic Lagrangian which well, is just the truncation of the Spirality Lagrangian. And what happens with the supersymmetric transformation? Well, we have that first, the transformations of the fermions become trivial because this maps 0 to 0. So this becomes 0. As sorry, yeah, the supersymmetric transformations of the bosons become 0, but the supersymmetric transformations of the fermions, even if we take them to be 0, that doesn't mean that they don't allow for infinitesimal transformation. Remain non-trivial. This is where one of the most important concepts in supersymmetric field theories of supergravity arises, and is the following. Suppose that I have a solution or a configuration which is of bosonic type. These guys have been reduced. I can wonder if when this is invariant under supersymmetry. When is this invariant under supersymmetry? Well, since we are on this bosonic background, this guy doesn't contribute, namely doesn't impose any question, but this guy does, even if we are taking it to be 0. So for this configuration to be invariant, this needs to be 0, and therefore this guy here needs to be 0. So a configuration that satisfies this condition for a certain spinor generator is called a supersymmetric configuration. Okay, and these are the equations that you get here are usually called the Killing spinor equations of supergravity, and they are generally a first order spinorial. And not only that, the main interest of these equations is that it is compatible or free, this is important, with the second order equations of the field. Equations of the field, mainly the second order equations that you get from the bosonic Lagrangian. These are complicated equations, nonlinear equations, as you know very well from your experience in gravity and general relativity, and they are very hard to solve, to analyze. Here, what we are saying is that simply because these theories are supersymmetric, they admit a certain type of first-order integrability. Namely, in some situations, solving this first order system of equations, which is much easier, gives you automatically a solution to the second order equations. And this is what people have exploited extensively. There are thousands of papers written about this. So why this is, or this might be interesting from the mathematical point of view. Well, one of the main reasons is the following. This. So let me just write this as a remark. Essentially, all systems of differential equations of relevance in differential topology namely Seiler-Witten equation, for example, those systems whose moduli space has been of relevance in order to address the study of the differential topology of low-dimensional manifolds. So Seiler-Witten equation, Donaldson equation, the Gromov equations of the pseudo-homorphicity, higher order or higher dimensional instanton equation. That's those for spin 7 instanton, in 8 dimension, instanton, etc. in 7 dimension. So all of these equations are, and many more, are particular cases of so the underlying thing behind all these equations, even if it's not apparent a priori, is that they are Killing spinor equations of a supergravity or supersymmetric theory, perhaps with a topological twist. We don't need to know about that now, but they are all particular cases of this type of structure. So clearly, this shows that it is worth studying this systematically. And this is what I propose to do. So now, let me give you an example. Enough with the general theory, which was just a schematic, just to give you an idea. So now we're going to consider a particular supergravity theory. And before doing that, we need to address the proper definition of the supersymmetry parameter, what I have been calling the supersymmetry parameter of this supersymmetry transformation. So let Ng be the pseudo-Riemannian manifold. This metric G is of signature P, Q. So P, Q, P pluses, Q minuses. And consider this manifold to be modeled on the vector space P. This is the vector space of the same dimension and the metric of the same signature. And fix a free module This is the key for algebra associated to this quadratic vector space. And these are the homomorphisms of some vector space sigma on which we are defining this moduli structure. So we will refer to this simply as this. Then we define a spinor bundle on and G is a pair of gamma, where S is a vector bundle. Okay. And gamma dimorphism of bundles of unitar and associative algebra, such that at each fiber, so this is the bundle of Clifford algebras that is canonically defined on this pseudo-Riemannian manifold. So at each fiber, if I restrict this guy here to the fiber, then I obtain another Clifford model. And the homomorphism now of this vector space. And I require that this guy is isomorphic as Clifford modules to this X. Okay, and then I say that this is a spinor bundle of type S. And now what I was calling a supersymmetry generator, I'm going to model as a section of such a spinor bundle for appropriate type. Now, what's the intuition behind this definition? So the intuition is that gamma defines Clifford multiplication, what people call Clifford multiplication, which is one of the most important or the most important property that a vector bundle that we want to call a spinor bundle needs to satisfy, because that's what allows to define a Dirac operator. So that's a fundamental property. So we have that on a spinor bundle, we have, as I was saying, this map. Sorry. It's a map of bundles of algebra. And on the other hand, this is an algebraic construction. We have a fiber-wise canonical identification between this bundle and the exterior algebra bundle, our underlying manifold. And using this all together, we compose this appropriately. We obtain an action of forms on a spinor by identifying a given form or polyform with an endomorphism of S. So now an expression of this type, so I take any form on my manifold, and now using this simple diagram, this expression, the action of alpha on a spinor, again, spinor is just a section of this guy. So this makes sense, because this is by definition And this is what is called free from multiplication. And perhaps some of you have heard about the gamma matrices that appear so frequently in physics textbooks. From this mathematical perspective, the gamma matrices are nothing but gamma matrices, right? This is just for some orthonormal covariant. This is a local orthonormal covariant. Okay, so hurry a bit. So, okay, now we know what's the right notion of a spinor that we need to consider here. And let me give you a particular example of supergravity. Which is one of the most fundamental examples. So example. This is for physical reasons, but because the physics is studied this before, they give weird names to stuff. So this is called Neveu-Schwarz supergravity. Neveu-Schwarz, actually. Anyway. And as explained before, by supergravity, just mean the bosonic sector and the Killing spinor equations. That's the type of structure that we are going to study. Because I didn't say before, but even if the full supergravity theory, as was saying, that doesn't admit a proper mathematical theory, the bosonic truncation plus Killing spinor equations, this does. You can develop a mathematical theory of that in the context of a standard differential geometry and topology, and that's work in progress. So consider this is in 4D. Consider for 6 4 manifold. And a pair of homology classes. Then the Neveu-Schwarz supergravity determined by this pair is as follows. So first, we need to we define this theory through the equations that it satisfies, that the equations of motion of the theory. So we have the Einstein equation. And as expected, this is of the type I was mentioning before. Ricci of Lorentzian metric. I will explain now in a moment. These are called the Maxwell equations. This is the Dilaton equation. Oh, and this is for variables. So the configuration space of the theory, mainly the space of variables are Lorentzian metrics, function, and 2 forms V, and we have defined four zones. Okay, so this is just this operation here is just a contraction of two indices within two indices free. So as promised, this is a type of equation that you could get in general relativity, but you wouldn't think of unless, well, there is some underlying structure, and in this case, it's supersymmetry. So you have Ricci equal to something out of which you can construct an NAT momentum tensor if you want to consider this in the mindset of general relativity. And then the other variables of the theory, functions, which are called dilatons, and these guys are called B fields, they satisfy their own equation of motion. And now, this is only one part. So now what are the clean-spin equations, right? So the clean-spin equations of this theory are as follows. Well, this is Clifford multiplication, precisely. That's why I introduced it before. So this is the action of a 1 form and a 3 form through Clifford multiplication on this spin-off. And this is the unique metric connection, so metric connection with torsion completely skewed given by HT. And section S with of type eta sigma, as I was mentioning before, irreducible type. So irreducible. So this is an irreducible Clifford model. So in particular, the spinor bundle in these dimensions, in this signature dimension is real and of rank 4. So this determines fully this spinor bundle, and this is the lift to the spinor bundle of the unique metric connection with torsion HP compatible with G. So if you have a triple of this type such that these spinorial equations are satisfied, you have a supersymmetric configuration. And if in addition these equations are satisfied, you have a supersymmetric solution. Okay, here I just said spinor lift lightly. If you recall, in the way that I define spinor bundles, I didn't even mention spin structures. Usually spinor bundles are defined through spin structures or spin C structures in complex geometry, but this setup is too limited for these applications to supersymmetry, because what you can prove is that for every such a spinor bundle as I define, there exists a spinorial structure which is called a spinorial mixed structure, which in some cases reduces to a spin structure, but it can be more general. This is just a quick remark that I want to do. And I studied this with my collaborator, Karin. We proved that in this particular case, which is 4-dimensional and Lorentzian, we go back to the standard setup, and every such spinor bundle, as we define it in this generality, is actually associated to a spin structure. So there is no novelty here, and therefore it makes sense to talk about this. Okay. Anyway, so now let's see what we can do. So now the goal, or one goal, is to classify in the appropriate sense, so using whatever hypothesis you want to use, the supersymmetric configurations and study their moduli space to see what it says, right? So for that, we need to use a framework that allows us to study these spinorial equations, as we have stated. So in more generality, one can pose now, motivated by this example, the following general problem. So we take mg of signature P minus Q equal 0 or 2 modulo 8. This is because we are dealing with real spinor bundles. This is important for supergravity, by the way, or supersymmetry. Complex spinor bundles are easier, but they are not refined enough for some of these theories. And the classification of real Clifford algebras is a classification modulo 8. So there are 8 cases. And of those cases, the simplest cases are 0 and 2, because these are real Clifford algebras of real type. And this corresponds actually to the cases 3,1, which is 4-dimensional Lorentzian, and 9,1, which is 10-dimensional Lorentzian. I think it's very important in supergravity and string theory, because these theories live in 10 dimensions. So we are lucky that the simplest case is also very relevant. And the fact that Clifford algebras are here real of real type, meaning that they are essentially, as unital algebras, they are essentially matrix algebras with real entries. So this is behind the fact that the spinor bundles in this case are just standard real spinor bundles associated to a spin structure. So I won't get into that. The point is that this type of a structure that we get in 3,1, we can just, for fun, consider it on every such signature. So we can do that generality. That doesn't mean that we are going to study those signatures, but it can be done in that generality. And then for that signature, then we fix this spinor bundle of irreducible type, and the system of differential equations that we want to study is just the following. The dHβ lifted to the spinor bundle equal to A epsilon, and so this is the general problem that one extracts from this theory, which covers that one as a particular case. Here, this guy is just in one form, taking values on the manifestations of S, and this Q is just an manifestation of S. This guy corresponds to, so this guy corresponds to this. This is our Q, right? And here, if you expand this in dHβ plus torsion, you get an equation of this type for a certain time. But this is the general setup. So now we need to address this type of equations, and for that we have worked out a geometric framework. This is work with again Cali, Vicente Cortés in Hamburg, and consists of the following. So the idea is comes from physics actually, and we have developed the associated mathematical theory, and is the following. What if we associate to every spinor of gamma S, we associate a polyform and we can do this in an equivalently, let's say. Namely, if you give me the spinor, I can get this guy, and if you give me this guy, I can get this spinor. And we can transport this equation as differential equation polyform again. Even. So this is the idea. And this direction is well known. The fact that you can take a spinor and construct what is called its square. So this is its square. It's called the square of the spinor. This is well known. But what was not known, and it's in a sense a difficult problem, is the opposite direction. So when does a polyform arises as the square of a spin? And this is what we are going to solve. And I don't want to erase that yet. You can see it here, right? So I need to hurry up a bit, but you know now what this is. But let's withdraw this diagram that we had before. Fixing our irreducible representation. This is the canonical identification that we have in monotheism. And now what we're going to use is that every such spinor bundle admits a compatible bilinear theory compatible with respect to Clifford multiplication, in the sense that it is either a symmetric transformation or a skew-symmetric transformation, and this guy is either symmetric or antisymmetric, and it is not degenerate. So using this, we are going to now construct a seemingly very naive map, which goes from actually from S into the homomorphisms of S. And this, let me call it like this, no, this. And this depends now on this choice. But this guy is essentially unique modulo constants. Well, there can be two choices in either case, but our construction will not depend on the choice in an essential way. So for every spinor that I will write now as this, do not confuse with this map, we now map this guy into an endomorphism. And this endomorphism is given simply in this way where this is the dual of this element by this map. So this is actually a seemingly very innocuous endomorphism because it is of rank 1 actually. But now composing this map with the inverse here, and the inverse makes sense because this is actually for this dimension and signature, namely for that signature, this is actually an isomorphism. So isomorphism of one of two associative algebras. Then we can compose with the inverse, and we end up with something that goes from S to the polyforms. Okay. And this is called the square of a spinor because here is like this is like sort of taking the square. You have this is a quadratic expression of the spinor. This is why people refers to this construction as taking the square of a spin. So, as I was saying, this we will just use this notation. This associates to a spinor to every spinor polyform. The point in doing this, by the way, is because dealing with equations for polyforms, differential systems for polyforms, is much easier than dealing with these bad boys here. So that's the idea. So now, for example, this construction, this direction is very classical, and you can even find it in the Michelson and Nonson spin geometry book, usually exploited in Riemannian signatures. Here, the Lorentzian signature might be much more complicated, but just to give you an example of this type of construction, for those of you that know about Riemannian special holonomy, there is a list, the Berger list, for the possible holonomy groups of irreducible non-symmetric Riemannian manifolds. And one case is the spin-7 holonomy case. And this spin-7 group can be defined as the stabilizer of a certain 4-form in 8 dimensions. 8 dimensions satisfy that constraint. So we can apply this construction. And if you apply this construction, this is well, in this case, it's an irreducible chiral spin, but never mind that. The associated polyform is precisely 1 plus this omega, that is the 4-form that is usually considered as to be present by spin-7 plus. And you can find this computation in Michelson and Nonson, modulo a global factor. So this is very useful because also, I didn't mention this map is equivariant with respect to the appropriate actions of the spin group. So this has been known in the literature, and now the question I was making before, I really need to hurry. Is the following. What's the image of this map? Inside the point. This is an algebraic question, so actually it can be posed at a point. And in order to address and solve this question, we need to modify the exterior algebra plot. Recall that here, this is an isomorphism of vector bundles, but this is not an isomorphism of bundles of algebras when you equate with this wedge product, because well, it doesn't preserve the product. But we can introduce a modification of the wedge product, which is called the geometric product. So we introduce a new product in the exterior algebra bundle, which we call the geometric product, and now it depends on the method. So this is depending on the method. And with this geometric product, this becomes an isomorphism. And this is the so-called Taylor-Antilla bundle. And this geometric product has a very explicit expression when you evaluate it on one form. So let's take this as a one form. Geometric product on any polyform. This is just wedge product and interior product of the dual. So with this modification that sometimes is called a quantization of the wedge product because it is a deformation, we obtain here an isomorphism. And using this geometric product, we characterize the image of this map as an real algebraic body in this linear algebra. So let me give you the result so we can think of some applications because unfortunately I'm running out of time. So the goal was to associate to every spinor a polyform and to transport this system of equations to equations on this board. And the result is the following. This theorem so then as introduced before our NG gamma is there exists a spin well, the equation that I have raised on this guy. If and only if there exists a nowhere vanishing polyform which satisfies the following system of equations. Satisfying. First, there are some algebraic equations which guarantee that this polyform is actually the square of a spinor, and these are as follows. These are alpha, geometric product alpha equal to 2 to the d halves the zero component of alpha. So this is a polyform, it has various degrees, so the zero component. Then alpha, beta alpha, is geometric product everywhere. Again, zero component. Sorry, zero component times alpha times alpha, such that this is different from zero. And finally, I 1 minus x over 2 composed with alpha equals sigma alpha. I will explain what that is now. So these are as you can see, these are actually polynomial equations for these polyforms. This defines an algebraic variety. And now we have, this deals with the fact that this alpha needs to be the square of a spinor, and now we need to consider the differential operations which are associated and are as follows. Is for every vector field. Let's evaluate this on a vector field. remember that this is a one form taking values on the endomorphism, so we can plug in a vector field. Now I need to check a sign because if I don't remember by heart, I should, but but for some reason, here you are. And well, this one is not differential, but it's easy to understand. So, well, several clarifications are in order here. So, this is the system of equations that we want to characterize. So here, this is just the standard, as I was saying, geometric product that I introduced before. This is the zero component. This needs to hold for an arbitrary polyform. It doesn't matter beta, such that the zero component is theta. And here, this is the canonical automorphism of the T4 algebra that acts as minus identity on the tangent space. And this is the canonical anti-automorphism of the T4 algebra that acts as the identity on the tangent space. And S is the symmetry of the bilinear beta with respect to T4 multiplication. And sigma is the symmetry with respect to if this is a symmetric bilinear form or a schizometric. So if it is a schizometric, this is minus. If it is a symmetric bilinear form, this is plus. If T4 multiplication is symmetric, this is plus. And if T4 multiplication is skewed, this is minus. Okay, and now this is just the polyform which is associated to the endomorphism. So I erased the diagram, but if you recall, to each endomorphism, we can associate a unique polyform. So everything becomes a system for forms, for differential forms. This endomorphism here just is represented in terms of forms. Everything, the spinor is represented in terms of forms, and you can equivalently study this problem just by studying this system. And you can forget about the spin geometry. You just study this system. And this, the fact, sorry, it's equal to 0. So this is just corresponds to this equation. So in order to finish, let me give you an example. I wanted to go further, but well, there is no time, unfortunately. So, but this is now a new perspective on this type of spinorial equations, which can be profited to study global issues of these equations, because usually what's difficult with the spinorial equations is to study global properties, such as the global structure of the solutions and the moduli spaces. So let me give you an example, and we can finish. So the class of differential geometric problems that arise in supergravity, and I wanted to discuss is that. So, and at least it reproduces the supergravity example that I wrote. It reproduces other examples. And well, let me give you two quick one example. So what the first example, I think it needs to be MG, 4D, and Lorentzian. So first of all, we fix our irreducible spinor magnet, blah, blah. So what's this guy? Finally. So if you can compute it, you can solve the system of algebraic equations fully. And this is of this type. Well, U is a null one form, never vanishing, and L is again a one form, but it is a spacelike and satisfies this condition and also this. So therefore, and actually, because of this structure, L is well defined. Modulo is transformation for a function F. So actually, a spinor, if you want in Minkowski space or in four-dimensional Lorentzian manifold, is equivalent to what we call a parabolic pair, which is a pair U and the equivalence class defined by this transformation, where, well, is not this level. Let's take like one and so this is, if you want, the first corollary that one can get from this theorem. Spinors in this case are equivalent to this type of one forms with this equivalence class here. And we can already apply this to examples of interest. The first example of interest is, how much time do I have left? A couple of minutes, perhaps. Okay, so the first example that one needs to study, which actually I thought was fully understood, but it turned out that it has very non-trivial global aspects, is the case of just a parallel spin. So if you apply now the previous recipe to this guy being 0, so you get that our manifold admits a parallel spinor if and only if this guy is 0 and this guy is equal to this expression for some anyone. So now we can study, we can forget that again about the spin geometry. We're going to study Lorentzian form manifolds admitting a parallel spinor just by studying this nice system of equations on one form. What else can you ask for, right? So we have exploited this system to prove various things. Well, we have studied parallel spinors and globally hyperbolic. Lorentzian form manifold. And one of the results, I just to mention it before finishing, that we can, for example, classify, we have classified all left invariant solutions. So assuming that the Cauchy hypersurface is a Lie group, we have classified all left invariant solutions. We have classified the differential or the diffeomorphism type of all compact surfaces, of all compact hypersurfaces. And which is without total vibrations over S1. And we have also studied the universal cover and other type of problems, which unfortunately I don't have time to discuss. But well, this is that just goes to show how this result can be even applied successfully to the simplest situation. This has been studied in mathematics with no regards to supergravity theory, because it's a very natural problem by itself, and is the simplest case of the previous supergravity example that I presented. And this, by the way, for example, gives you for free the condition that a manifold admitting a parallel spinor in the signature is automatically Brinkman space. And well, I will finish here. Thanks a lot.
So you mentioned that your initial equation was compatible for free with the equations of.
Yes.
Can you please clarify what you exactly mean by that?
Yes, that's actually a good question, because suppose I have some, well, suppose I have some second order equations, complicated for various objects. If now I want to think of some first order, these are second order, right? Now I want to think of some first order equations whose solutions automatically satisfy all these equations, or at least a big chunk of these equations. If you just want to do that, sitting on your desk, you are in general not going to be able, because well, you have to inspect this, and well, I don't know of any constructive procedure to do that. What I mean for free then is that these equations, you don't get them by imposing that they are first order integrability conditions of these equations. You just obtain them from the supersymmetry transformations, which were obtained via a completely different mechanism that has nothing to do with that. You check a posteriori that actually these equations that come from this supersymmetry transformation have this property. But the people that constructed these supersymmetry transformations were not thinking about this. They were thinking about Lagrangians that can be invariant under this type of transformations and what type of transformations you can get. It was later that people realized that you can do this, and this has been exploited extensively in the literature to find some type of solutions that were thought to be impossible to be found analytically before. And actually, I have I had various discussions with people that didn't even believe that such type of solutions could be constructed. One of them, Pembroke, by the way. I had a long discussion with him. He told me he couldn't believe this type of black hole solutions coupled to matter could be found explicitly, but it can, and it's thanks to these supersymmetry conditions.
Okay, but the solutions to the first order equations need to solve all of the second order equations.
If you want them to be proper solutions, yes. So
it isn't necessarily so the case.
Come again, sorry?
I think there was a situation before in which you mentioned that you have a solution to the first order equation, and then you have to impose that they solve all the second order.
Yeah, because in general, solving the first order equations doesn't guarantee that all are. But for example, in Riemannian signature, which is where people are, mathematicians have usually dealt with these systems, it is guaranteed in general. So you don't even have to mention this equation. And a particular case of these first order equations that has been studied by mathematicians, by Zhao and other people in complex geometry, is the Hall-Strominger system. This is thought to be as a natural generalization of the Calabi problem to non-Kähler complex geometry. And people study this system, and this system comes actually from Killing-Spinor equations in supergravity, but you don't care about the second order equations because they are automatically satisfied. But in Lorentzian signature, that's not the case. It's a bit more complicated. Sure.
Just trying to understand your equation, you said that you're using the Levy connection plus torsion, right?
For the example, yes.
For the sample.
For the example, yes.
Right. Because I was thinking of a natural case is when you have a partial manifold, which is a manifold with a Levy with a metric and a connection, which is not a Levy connection. And under certain circumstances, certain hypotheses, you have the Mises theorem, which characterizes all these connections with torsions as three forms. But you need the space to be a symmetric space. The metric should be Riemannian.
Okay.
So you know about it, or
I didn't know about that, but what I can say is that the example of supergravity that I mentioned, which is fundamental one, essentially almost everything remains to be explored. That's actually a system of equations that should be studied properly in pseudo-Riemannian geometry with torsion. So, but I didn't know about that result. The thing is that about the Lorentzian case, little is known. In the Riemannian case, much more is known, and perhaps, well, some people who look that have studied this system is clear in the past. Pica Agricola also as well. Ivanov, they have explicitly studied the system, the supersymmetry system, and they have many results. So perhaps in the purpose there is some in Riemannian signature. Lorentzian signature very good.
Thank you.
Gracias.